Yeah, I record from now. Sorry. Yes, because I stopped before. Yes. Okay.
I mean, if you, of course, you can have my PDF slides. I will make it available, so maybe that's okay. So I don't think I need to restart now, no?
No, not for sure. I mean, we registered the previous one, so for this one will be okay, the PDF, no problem.
Okay. So let's see about the effect of the magnetic fields that we completely ignored to be simple and to make sure we could write up a very simple expression very quickly. So we have a cloud and we have magnetic fields. This is a very typical situation. You always have this. And if you look at the Planck maps, if you look at the near-infrared maps and polarization maps, you see that magnetic fields are everywhere. And if clouds are especially, say, magnetized, you tend to have parallel magnetic field lines on top of the cloud. So this means that the magnetic field is affecting the dynamical evolution. How does it do that? Well, I mean, in this case, you have to think that your cloud is a mixture, overall neutral, but it's a mixture of neutron molecule, electrons, and ions, so positively charged particles. So you have charged particles, and this charged particle, as we saw in this picture of the cosmic rays that were gyrating around the field lines, you have the same thing here. You have actually the ions that are linked. They feel the magnetic field, they want to just stuck on it. And they are behaving differently from the bulk of the material that is neutral. So now, what is the force due to a magnetic field? So the force of the magnetic field is like, you know, you can consider that as like a pressure term, and you have an area. So here you have R square and times B square. And you can understand how this comes through because you have to remember again from high school, the force on a wire. So you have your magnetic field force that is I, so this is the current in ampere, times the length of your wire cross B. So this should be a vector form. And I, so the current is proportional to the length of your wire times B. So if you put these things together, you see that you have R square, B square. So the fact that you have ions that are spiraling around these magnetic field lines, in principle means that they are kind of freezing the magnetic field into the material. And of course, this freezing can be more or less true depending on how many of these ions are present. So if the ionization fraction is very large, then basically all the cloud will be stuck in there because of course the neutral will also feel indirectly the effect because they will collide with these ions. And if you have magnetic fields standing there like, you know, very, very strong poles that you just don't go through, you know, it's like to have a very strong force that is counteracting the contraction motion. So what happens is that there are the neutrals that want to contract, but there is this magnetic tension that actually acts in the opposite direction as to the force. So what happened again, as we saw for the rotation, you end up with some sort of flattening here. So you end up with a cloud that basically flattened. So let me just go back a second here. So it flattens, can contract along the magnetic field lines because here there is no problem. You can just go through, also the ions can be squeezed, but in the other direction, perpendicular, it will be much more difficult because there is this magnetic tension pressure term that will end up. So what's happening? So in this case, if we have, assume that you have actually the magnetic field really frozen, but you know, you have frozen in due to the presence of these ions, and the neutrals are pushing, you know, you start to keep, how to say, squeezing the magnetic field toward the center. And this is the case that we call like ideal type of ideal magnetohydrodynamics. So you have like basically that there is no slippage between neutral and ions, and you just squeeze the whole things together and you end up in a geometry like this with curved magnetic field lines. Looks like some kind of hourglass shape that is in fact seen in star formation. But if magnetic field is really frozen, then this means in physical terms that the flux must be conserved. So the flux is B times R squared, must be conserved. So this means that the force due to the magnetic field is proportional to R to the minus 2. This is because you have this flux constant, so B is proportional to R to the minus 2. And if you remember from the previous equation, you end up with this proportionality term. So this means that now we have a term that has exactly the same term, say the same dependence on R as the gravitational force, which means that in fact magnetic fields in this frozen, status, even they cannot overcome the gravitational force. So is in a sense, it's not as strong as the rotation, you know, for the when we saw before the angular momentum problem. They can, of course, retard, but they cannot completely prevent the contraction. And we can also do the same exercise as we did before for the case of the angular momentum to see how much, so if you just squeeze all the magnetic field in the center, so you maintain this flux, magnetic flux constant, what is the value of the magnetic field there? So again, if it is constant, the magnetic field, so the flux at the star location, assuming that you are forming a star while you contract, the flux at the star should be the same as at the cloud. So you have B star R star square equal to B cloud times RC square. So this means that if we take, for example, a cloud, you can put any number here, just put random numbers, like a 30 solar mass genes cloud with the radius of, it doesn't even mean need to be genes, it's just that it has to contract anyway, so super genes in a sense, with the radius of 0.3 parsecs and an initial, this is another unit that you may not be so familiar with. Well, at least astronomers are not, because we always use the Gauss, but you know, there is a correlation between the two, the Tesla and the Gauss. I think it's a nano Tesla that is equal to a micro Gauss, so you can do your conversion. So here you have that if you start with the B cloud of the order of 1 nano Tesla, which is, say, observed to form a single star, then this expression here gives 1,000 Tesla, which is huge. You know, even the sun magnetosphere, at the magnetosphere, has a magnetic field of the order of between 50 and 400 micro Tesla. So this is again, you know, a humongous number that something is wrong. We need to again get rid of this magnetic flux during collapse. So there are still two things that we need to lose, angular momentum and magnetic flux. And now we come to the ambipolar diffusion that in a sense solve this problem, at least for the magnetic flux problem. Because now, what is this ambipolar diffusion? Again, if you consider the ionized component and the neutral, now the greens are the neutral. The greens, as I said, that they want to go through these magnetic fields because they feel the gravity, they want to contract, they want to collapse. If the cloud is, say, is above, so it is, say, out of equilibrium, it is wants to collapse, they want to go toward the center. But then there are the ions and neutrals that are linked to the magnetic field lines. So what happens is that the neutral will actually collide with these ions that are fixed to the magnetic field lines, but eventually with the time, the material continue to grow toward the center. So the collapse is a bit slowed down, and compared to the dynamical time scale that we saw before, free fall time scale, We talk here about the factor of 10 slowing down for typical numbers of ionization fraction that we have in these clouds. So neutrals can slip through, so more slowly, but can still go through. So this means that in a sense, if you are like a neutral species and go through, you basically see the magnetic field passing by, and you are accumulating more and more toward the center. And this means that the central region where the material is accumulating becomes less and less, magnetically, so the flux basically is lost in some sense, because it's like expelling the magnetic field lines toward the outer part. And this is basically the simple way to describe, say, the ambipolar diffusion. Of course, you can do this with the equations, doing the collisions between the ion and the neutrals, including the gravitational terms, and et cetera, but at the end, I mean, the main thing to remember is that you expel the magnetic field lines, so the central part can actually contract and then form a star. And this is important also for the, in a sense, angular momentum. So if we go back to the angular momentum problem, and it's still present in a magnetized cloud because it is still rotating, contracting, and then there is also the magnetic field to take into account. So the problem becomes quite complex. So that's why I wanted to do one piece at a time. So the angular momentum can be lost, say, during the contraction, for example, by fragmentation, because you can transfer the angular momentum to pieces of your cloud. So, you end up with pieces that individually have, say, smaller values. You can actually also do an angular momentum transfer, for example, to the surrounding cloud, if there is some link also, say, with the magnetic field. There could be some, transfer to surrounding material. But another important, mechanism is through the magnetic braking, is called, and this is very important also for the formation, actually, of the protoplanetary disk, as we will see in a minute. So the magnetic braking is, to understand this, you just have to consider, again, consider these magnetic field lines that are getting a bit squeezed initially, toward the center of this contraction, although you have the slippage of the neutral through them, but still you have some, at least initial, say, squeezing of the magnetic field lines. So in this case, what happens? If you consider, so this is actually a figure coming from the Staller and Palla book, that I think beautifully explain the concept. So this is your magnetic field line. If you have a, say, material here that is rotating in your cloud, and the material is in a sense linked to the magnetic field lines because there are some ions that are frozen into the magnetic field lines, and then the neutrals actually collide with it. So what happens is that the field lines tend to kind of follow the rotation together with the material. So the rotation is actually going into the page here, so into the page here. So you have this rotational velocity toward the page. At the same time, because the magnetic field is bent in that direction, you then, action and reaction, you then get this force term from the magnetic field, because the magnetic field line wants to go back to the original shape. So you have this magnetic force that counteracts the rotation. So you see that in this way, you can actually slow down your rotation and then consequently lose the angular momentum. So basically, as I wrote here, any spin up during collapse can twist the magnetic field line, increases the local magnetic tension, and then, of course, this tension creates a braking torque. So you decelerate the motions and you lose angular momentum. And this is just to get us, say, in the current stages, we see that this is a very important process for the formation of protoplanetary disks. And in fact, this is the work from Bo Zhao, who actually he left today. He's going to Canada now to work with Raf Pudritz, but he has been with me in the CAS group for several years, and he has been working on the contraction, in fact, of magnetized clouds with some rotation. And we have seen, for example, that depending, so it's the whole process of protoplanetary disk formation is very much dependent on the microphysics. So for example, if you have very small grains that are present in the interstellar medium, these very small grains can carry charge, negative charge, so they are actually very conductive, so they are actually linked to the magnetic field lines and tend to push the magnetic field lines inside the cloud. So this means that you have a relatively high magnetic flux toward the center, and these can slow down the rotation even too much, to the point that actually the angular momentum is almost completely lost. And if you have no angular momentum left, you don't form any protoplanetary disk, because basically you end up with the material just collapsing onto the central star. But if you get rid of these very small grains that carry charges, for example, through a process that is similar to the freeze out of molecules, you can actually form self-gravitating, relatively massive disks. So it is all depending on this microphysics. And this has been, now we are going into the three-dimensional non-ideal MHD, and I'm not going to, I don't have the time to go into that, but if you're interested, you can actually see these first two papers of Bo Zhao and the collaborators. We also have some newer paper now where we include other non-ideal effects, so not just the ambipolar diffusion, that is actually basically the most important thing for the planet, for this protoplanetary disk formation, but also other non-ideal effects like the ohmic and the Hall effect, but I'm not going to tell you. So here is just to show that without, unfortunately, these movies are not working here with the PowerPoint, but this is the end of the movie. So without the very small grains, you can actually form disks, but with very small grains, there is no disk left or formed at all. It's interesting that his simulations, just changing a little bit, for example, the cosmic ray ionization rate, etc., you can form with this simulation structure that in fact have been seen recently. For example, Laura Perez with her observations of disks with spiral arms, or for example, John Tobey, who observed this multiple structure in a young disk. And we can form that just changing a little bit, say, the parameters. Okay, so to summarize this part, I would say that it's important to remember that rotation can halt the collapse perpendicular to the rotation axis. Remember the centrifugal force versus the gravitational force. This leads to a formation of a disk. The angular momentum needs to be lost. Magnetic braking is one of the major ways, say, to actually lose at least some of this angular momentum, but you don't want to lose it all, otherwise you cannot form protoplanetary disk. You can transfer angular momentum also in other ways, but it's, say, the most obvious in these magnetized clouds is most likely the magnetic braking, unless you are in a big cluster or more, say, complex environment where you can have exchanges, tides, and things with the material surrounding. Magnetic fields cannot halt the collapse, but they also lead to flattened structure. Again, we need to lose the magnetic flux, otherwise we get to too high values of magnetic flux toward the center that are not seen. So for this, we need ambipolar diffusion, so this slippage of neutrals through ions that are stuck on the magnetic field lines. And then finally, we form our disks. So now so if you have some question, again, just interrupt me here and ask me. Otherwise, now it's getting a bit more descriptive because I will show some pictures and there is basically very little, let me see, I check. I think, yeah, there is not much, say, it's more like observations than theory. But anyway, stop me anytime. So I'll just go with some pictures that, of course, will link us also to the lecture of tomorrow. So these are some examples coming from scattered light. Sorry, this is just reflected light. Yeah, scattered light from disks. You see in some cases jets in the optical, and for this you have actually to be in a relatively evolved system where you basically get rid of the mother cloud of the envelope, otherwise you cannot see these short wavelengths, of course. But you see the disk is here, and you see this, it looks like some kind of flare disk, and then you see, like looking inside the plate, you know, you see the like a bowl here, here, and here, and the same in these other clouds. Here is an example of disks in the Orion. This is seen in, say, silhouette. These are silhouette disk, and you can see the dust absorption. This is actually a line composite image where you see some scattered light, reddish light from the young star in the center. So it's getting red by the same effect as our sun getting red when it's setting. So I found this actually image very, very nice for this, because there is some reminiscent of what's going on sometimes in cloudy, relatively cloudy sunsets. And then, of course, we arrive at this beauty that is the HL Tau disk that was imaged with ALMA in 2015. And now with ALMA, you see all kinds of details. You have not just your flattened disk, but you start to see rings and structure, asymmetric rings, little, you know, rings that get bigger on one side, smaller in the other. They're very complex structure. And you can see this is at 1 millimeter, but you can see it also with the JVLA, so Jansky, the very large array in New Mexico. And here, the beauty about these observations, so this is again the ALMA, but then this is the 7 millimeter. So with the JVLA, you can go at longer wavelengths. So now you're sensitive to, say, the larger grain population. So you can make comparison between the 1 and 7 millimeter emission and actually say something about the presence of large grains in this disk, because this is the thing we will see tomorrow. So grains will actually end up becoming big, and then, you know, you have to make planets big things. So we have to have something like the Earth where we can sit down and go around and live. So it's there is a lot of processing going on. Just to give you some more example of this beautiful structure, different one from the other. Again, I think really telling us that the initial conditions and the environment is very important, and the little things also in the microphysics can give you this final structure of your disk. So you see something with the spirals, large gaps, tiny dust rings, and things without rings. You have the zoo here of disks, and this is of course the disk substructure, no, what is called the disk substructure at high angular resolution project that is was PI'd by Sean Andrews, and there are many papers on this survey now on Astrophysical Journal. One thing, again, self-advertising, because this is work coming from the group, the CAS group. So the work by Dominic Segura-Cox that has been recently accepted by Nature. This is now, you see, this was the HL Tau that I showed you before. And this is like a relatively old class 1/class 2 disk. Now, with Dominic and Alma, she was able to see this ring structure in a much younger disk. This is like a class 1 disk, is still very much embedded into the cloud, mother cloud or mother core. And you can already start to see this structure. So this means, so the message of this paper is that actually these rings that most likely are telling us about the formation of planets, they are really too regular to tell us about something else. It's probably, you know, due to some process that in some sense promote the formation of the planet. So planet formation must start quite early. And this is something that I think is a new message, that it's important because people tend to focus on formation of planets in these more evolved disks that are present in later stages, say of star formation, where there is no molecular cloud anymore. So this is something to now rethink about this, and planets and stars are most likely forming together at the same time. So yes, because now I have talked about class 1, class 2, I just want to, for those of you who are not so familiar about this nomenclature, I wanted to actually, oh, this is not seen very well here, but I think it's seen well enough. Again, it's not needed to look at the details, the numbers, but just to understand. So in star formation, we, and this is mostly an empirical subdivision here, depending on how the spectral energy distribution, which is this lambda, f lambda, this is the flux at a certain wavelength as a function of lambda, looks like. So if you have a very, very early stage star formation, your SED is peaking at a quite long wavelength. And basically you just see the envelope, the cold envelope, the 10 Kelvin envelope. You don't see much in the central region. But with the time, so you have, of course, a protostar that has also outflows, as we will see a few minutes later. It will start to, how to say, dissipate this core surrounding. So you start to see more and more toward the center, and your SED becomes actually skewed toward shorter and shorter wavelength. So there is a stage in which you have a mixture of envelope and actually some envelope dissipation, and this is the class 1. And then once you have the complete dissipation of the envelope, we are in the class 2 stage. Now we have a central star that is not even anymore called protostar. Now it's a pre-main sequence star. So it's a star that actually its luminosity is not just coming from a shock accretion as previously, but it is actually coming from deuterium burning. So it is on its way toward the main sequence where actually hydrogen, so the temperature and density will become large enough, at least for those stars that have a high enough mass to do that, to burn the hydrogen. And then class 3 is when actually the disk is started to also dissipate, because you have start to have also formation of planets and big holes, big regions where are devoid of dust, and then you have basically the stellar SED, spectral energy distribution. Right, so again, if you have questions, ask me. Otherwise, now I will explain just briefly, I think this is also an important point for star formation, about this shock accretion, because I said to you just now that during this protostellar phase, protostars actually are not self-luminous in a sense that they are producing energy from their center through nuclear fusion. The luminosity is mostly due to the accretion. So just let me elaborate a little bit on this point. This is what is happening. You have an outer envelope, and you have the collapsing, and you have a central region where you actually start, so the temperature is increasing and the pressure also is increasing. So it gets to the point where at some point it will get this nuclear fusion, and starting with the deuterium burning. So in the protostellar stage, no deuterium burning, so the luminosities come from this shock. So where does this shock come from? Well, it comes from the fact that you have contraction, And at some point, this contraction must end because you reach the surface of your protostar. So this is where the shock happens, okay? So you have this material raining at free fall speed in these conditions here. So the velocity is very, very large when it gets to zero, basically at the surface. So all this energy, this potential energy has to be transformed in basically kinetic energy. And what happens here is that it becomes radiation energy, okay? So let me just go to the, say, few equations that you need to remember here. So we can derive the accretion luminosity, in fact, from these simple equations. So once, the thing you have to do is to get the free fall velocity. And you can do that considering the kinetic energy equal to the potential energy. You see, this is the free fall velocity here. So the free fall velocity gets equal to 2gm over r to the square root. Assuming that the shock is at the surface of this protostar, Rs, and that most of this kinetic energy is converted into radiation, you can estimate your accretion luminosity by this expression here, 1/2 VFF square times m dot. So m dot is the dm over the t. So in this case, you can then use this expression here with small m as m dot. Just these two things are the same. And the m dot is the mass in fall rate. This is the same expression as it was in the previous page, just for you to remember. M dot is equal to 4 pi r square rho v. You can again get this from the usual expression of the spherical cloud. And so if you have a constant, assuming a constant m dot, you immediately can know what is the velocity profile and the density profile of your cloud, which is quite cool, no? I mean, you expect, if you have a constant m dot, you, from these equations here, and assuming constant m dot, you can immediately derive that the velocity must go as r to the minus 1/2, which more or less is, in some cases, is what we see. And also the density goes as r to the minus 3.5. So this is again something that it's good to remember. And if you see deviation from this, it means that probably there is not a constant m dot, which is interesting. And the other thing now that it becomes interesting, and I just wanted to, if I can have a few more minutes to go through this, it's not very, just tell me when I should stop. I would like to tell you how you can actually proceed with this continuous contraction, because after all, I just told you that, okay, if your fragment become opaque and they cannot irradiate too much, you cannot really, at some point you become hydrostatic, it becomes in hydrostatic equilibrium, so you cannot go cannot squeeze much more. So what's going to happen? How can it become a prime sequence star? This little ball of warm material. So as the hydrostatic core heats up, so there is a potential for further collapse. So let's see this potential. So we can just recall the Jeans mass. If you remember, the Jeans mass is proportional to, you should know this now by heart, T to the 3.5 times rho to the minus 1/2. And so to have marginal stability, you can say, you see, always back to the envelope calculation, you can say that so these two must balance, so T to the 3.5 must be proportional to rho to the 1/2 to have marginal stability. We can rearrange this to avoid the power on the temperature, so you see that T must be proportional to rho to the 1/3. We can now start to introduce this gamma, which is the polytropic index. And so I can put this as gamma minus 1. And gamma is now here equal to 4/3. So basically we are saying here that if gamma is larger than 4/3, then the Jeans mass will increase with the temperature. and the core then is stable. However, if gamma is less than 4/3, then the Jeans mass will decrease when the temperature increases. So then you have further collapse. So let's see what happens inside this protostar. So you have this hydrostatic core that is accreting material. Temperature and densities are increasing. So there is something that is going to happen that we have not talked about, but of course you have dissociation of H2 molecules because it becomes so hot that basically you have enough energy for each collision of the molecules to actually break the bond that I already mentioned is about 4.5 electron volt. Does this affect the stability? Because in fact, I mean, one can think, oh, going from molecular to atomic, maybe there is something going on. So we can look at this, that's why I introduced the polytropic index, because this is linked to the type of material that you have. It is molecular or it is atomic that changes. So we just said before, if gamma is larger than 4/3, then the core is stable. If gamma is less than 4/3, the core is unstable. So let's see, if you have H2, so it's a diatomic molecule, you know that gamma is the number of degree of freedom of the molecule, which is 5 for a diatomic molecule because you have the vibration, the two rotation the two rotational motions and the translational motions. Unlike for the monatomic gas where you only have the 3 translations. So you have here that you end up with gamma that is actually 1.4, which is larger than 4/3. So if H2 remains H2, you have a stable core. If you get to the atomic phase, which is the case because you reach a temperature that is above, say, 2000 Kelvin, then you have to change your F with 3 instead of 5, and you get 5/3. This is still larger than 4/3. So in principle, this is not what is triggering the this extra collapse. But we forgot about a little particular thing. And the little particular thing is that the process of H2 dissociation takes energy. I told you, it's 4.5 electron volt. Where this energy comes from, if not from, the cloud. There is nothing else. I mean, there is conservation, must be conservation of energy, at least here. So this energy that requires the dissociation of H2 is the thing that triggers this second step toward the contraction of this core, this first hydrostatic core that then can go toward, say, higher and higher density. So you have the second shock front, and you can continue to accrete material. And of course, there is some kind of, runaway process. So this is a terrible slide because it's an old picture, but I cannot find a more modern. I probably should make it myself. But anyway, the thing is that the central temperature here, as a function of number density, this is all what you need to know. So there's a 10 to the 2. So starting really from the molecular clouds down to the sun, basically. So you see at the beginning, you have this isothermal phase. It summarizes basically what we have said so far. Isothermal phase up to some density. Then you have the optically thick phase, and you start to have your first hydrostatic core. This keep heating because it's basically optically thick. Oops. And then until the dissociation of H2, which then triggers a new collapse. Then you have the second collapse phase. And then you have the continuous accretion of material until you get the nuclear burning, and you can even arrive at the sun up here if there is enough material that the core is accreting. So so this is the last point that, in fact, I mean, I probably don't even need to cover if you wish, is about the feedback. And actually, this is the same picture I started with. So once you have this formation of a protostar, what happens is that the protostar also have outflows. And again, is mainly observational. So if you wish, we said, you know, until 4:30, I'll be happy to be here, unless there are questions, of course, that it's more important to answer. But if not, I would just show some pictures of these outflowing regions.
Right, we can ask to students if they have questions, then we will see if we will still have time.
Yes.
So.
Hi, Paola.
Hi, Giovanni.
I actually have a question for you about the mass accretion rate that you discussed a few slides ago. And I was wondering if, are there any observational constraint to evaluate this quantity? Because I can image that the simple evaluation of the line profile can be not so trivial, right?
Yes. So this is, so you can do it with, for example, so you're talking about, say, the accretion onto the protostar now, no?
Yes.
So that then gives you this accretion luminosity.
Exactly. That drives the chemistry and exactly. A lot of things around the star, right?
Right. Yes. So of course, yes, this is not easy because you want to measure, I think it's, how to say, in a sense, model dependent, but you can try to do it in the following way. So you can, for example, it has been done in a sense with the water lines, with Herschel, for example, because some of the water, of course, come from the, say, outflow, but you can also see these beautiful, say, inverse P-Cygni profiles that tells you the infall velocity in the inner envelope where you have, say, high density material. So you can actually try to reconstruct that with the model. And of course, you only have the radial velocity here. But yes, you can at least have a model of that can tell you the radial infall velocity, and then you can, in a sense, extrapolate to the center of the star. Because unlike a starless core, where the infall velocity at some point just stops because you have this, you have not the protostar yet. In the protostellar case, you can, in a sense, assume that you have a continuation of the infall, at least in the region where you have the disk, because that's the other complication. You have also material that is landing not on the protostar, but on the disk. And then, of course, you have also accretion from the disk. So, but to simplify things, if you can do, say, accretion from the envelope onto disk and protostar, so you can extrapolate, in a sense, from that. Other things you can do is to indirect, is from the outflow, because the two things, of course, are related. So the infall should be linked to the outflow. There are, in fact, some relations. And if you can estimate, for example, the momentum of the outflowing material, you can also estimate, in a sense, the accretion material. And then you can kind of, estimate this accretion luminosity. But the only thing is that you have the luminosity of your protostar, and then, you know, you can, in a sense, derive from the equation that I show you what should be the expected, assuming that you have a size of your, say, protostar relatively well known. And this again comes from models, because we don't have enough angular resolution at the moment to see at that, but at least at these long wavelengths that we have to use for these early conditions of star formation. So you can actually do the inverse problem and look at the accretion luminosity measure from the continuum, say in the mid-infrared, near-infrared, if you can, and then once you have the luminosity, you do the inverse problem and get your free fall velocity, in a sense, at the shock surface, at the surface of the protostar. But again, there are lots of, how to say, assumptions that you have to make. You know, it's like our example of the spherical cloud. In a sense, it's the same thing. If you can make some assumptions and be happy with that, you can approximately know
that value.